Thank you for joining us for this installment of the TPM Manufacturing webinar series. Today's presentation is titled Innovative Design Strategies for Additive Manufacturing. My name is Scott Gvozdas. I am the 3D Printing Account Manager at TPM. Our presenter today will be Justin Hopkins from Hewlett-Packard. Before we jump into the webinar, I just want to quickly go over the webinar format and an overview of TPM. So on your computers, you will be able to submit questions throughout the presentation. We will address all questions at the end, so as things come up, go ahead and just type in your questions there and we'll be able to field them at the end. Quick overview of TPM. So we are a family-owned business. We've been in operation for over 45 years and we're headquartered in Greenville, South Carolina. We have 6 locations spread throughout the Carolinas and Georgia, and as you know, today's webinar is focused on 3D printing, but we also support our customers in other areas. Those being on the software side, we work with SolidWorks and Autodesk. On the hardware side, we supply office copiers and plotters, and we also support our customers with printing services like trade show graphics, wall murals, and architectural plans. Our presenter today, as mentioned, is Justin Hopkins. He's an applications engineer from Hewlett-Packard. In this role, he works with companies to help them reinvent their manufacturing process through the use of technology. Prior to HP, Justin spent 13 years in the education and design field as the rapid prototyping operations manager at Savannah College of Art and Design. I want to welcome Justin.
Thank you, Scott. So today, before we begin in some of the strategies and design things that you should do when you prepare a file for printing on HP MultiJet Fusion, we're going to go a little bit over the process of how the system works, just so you have a basic understanding of how the technology works, and then why we apply some of the strategies that we do to parts in order to get good results. So as you can see right now, the system itself uses a multi-agent process in order to fuse the parts together. So essentially what we do is we disperse 2 different types of agents across a bed of powder. And one is referred to as a fusing agent, which is outlined in the black droplets that you see on the left-hand side. The other one is the blue agent or translucent agent, which would be a detailing agent, which gives us nice details and cools off the part as we print. The technology works with print heads. So we stagger 3 different print heads across a print bar, and then we essentially do 2D printing, right? We disperse the agents just like you would on a piece of paper, and in those locations at the same time where the droplets are dispersed, we have infrared energy that follows that, which applies it to the powder, and it's absorbed into the agents, mainly the fusing agent, which is actually black. So if you think of it as like a black car outside on a hot day, it absorbs a lot of heat. So it's going to be, the energy is going to be attracted more into the areas where the fusing agent is, which brings it above the melting point, and then the part melts, and then the bed lowers, and then that process repeats itself over and over and over again. And in between each pass, we cover each layer with nylon powder. And as I said before, that repeats itself and the bed lowers, and then you're left with a fused part. So just quickly as we go from the left, we disperse the agents. We follow that with infrared energy. The bed lowers, where you have the fused, or where the agents are applied, you have the fused part, and then we cover that with powder, and then so on and so on. One thing that we'd like to point out is that even though it is a print head based system, it is different than other technologies that use print heads in order to make final parts. On the left-hand side, one major confusion is people refer to it as binder jetting. HP MultiJet Fusion is not binder jetting because we're using a thermoplastic and the part is actually fused. So when the parts come out, you have a fully functional part without the need of infiltration of the parts afterwards. So when you think of binder jetting, they are using 2D print heads, but they are using essentially CA glue in order to bind the parts together. On the right-hand side, you have material jetting, which uses UV light in order to cure thermoplastic, essentially acrylic-based materials. So very similar in the process, except for you're dispersing the material down onto the bed as opposed to the MultiJet Fusion, which the powder is the bed. So it's a little bit reverse, and the materials are very different in their properties. Hold on one second. So as we said before, the technology is based on what we've leveraged from our 2D side, which is our 2D print heads that we've now put into a thermal process. The print heads, as I said before, there are 3 staggered across the print bed, which allows you to get a lot of detail and a lot of speed, because when we make one single pass across the print bed, we cover the entire printable area in one pass, as opposed to other technologies which may be a point-based system. So here's a little bit closer look of, the entire print area is where the gears are. The print bar that we spoke about before contains the print heads and the energy. And in one single pass, you can print whether it's 1 part or 1,000 parts all in one layer. The timing is all based on speed and vertical inches in the print area. The types of materials that we process are polyamide, semi-crystalline materials currently. The reason we look at semi-crystalline materials for our process is the fact that we are moving very rapidly and quickly throughout the process, so we have a very small amount of time in order to fuse a part. So semi-crystalline has a very defined point of where it melts, as opposed to like an amorphous material such as ABS, which has more of a range of where it melts. So the types of materials that we focus on are semi-crystalline currently. And then one major difference in between technologies is we're most commonly compared to SLS. And SLS gives you a very similar result of part in the end because it uses polyamide materials, and the polyamide materials are fused with a laser as opposed to ours using infrared energy. The SLS process uses a point-based system, so you have to raster out the entire area of a part, which takes much longer point of time, as opposed to the MultiJet Fusion, which does the area-wide pass. What this is denoting right here is how long we take to fuse. SLS is faster in the fact of where they fuse, but it takes much longer in order to build a part because you have to raster out every single layer as opposed to the area-wide pass. So we take longer to fuse, and what that means is in the end, you have a denser part off of an MJF part as opposed to SLS, even though the material processing may be very similar. And now we're going to move into design strategies and processes. Why is designing for the process very important to any manufacturing process that you're doing? You wouldn't want to take a design process for, let's say, CNCing and then transfer it over to 3D printing. You need to design for the process in which you're using because you can then take advantage of the process that you're trying to do. In addition to the fact that if you design for the process, you get better tolerances and better parts. And a lot of misconception when it comes to 3D printing is design freedom doesn't mean that designers don't need to abide by certain rules, right? 3D printing does give you a lot of different options, and the fact that we can break some of the rules that you would see in injection molding or any other type of technology for manufacturing, but that doesn't mean that designers still don't need to follow some basic rules when 3D printing. The reason we use this slide is our process is very similar to injection molding in the fact that when we go and process the polyamide, we're entangling the layers of the plastic, which is very similar to injection molding, which gives you a very dense part and allows you to achieve the best characteristics of the polyamide material. But even when you're considering injection molding, there are certain rules in which you need to abide by in order to get basic parts. And the same thing applies for MultiJet Fusion. When we move into MultiJet Fusion, as we said, we use infrared energy to fuse the parts together. One of the parts of the system is a closed-loop thermal control camera, which is based on the top of the machine, which reads the temperatures across the bed. And this allows us to see where hot spots are and cold spots are of the parts that are being printed, and allows the machine to adjust the bed temperature as it prints throughout the build. But when you look at this, you have to think of designing parts and looking at it layer by layer, because what's happening on each layer affects the parts. So when we look at this example here, it's basically like a typical housing part. If we look at the very top part in the purple, typically people design orthogonal walls because that's what they're used to. They think in 90-degree sections, and so typically a designer would design a housing such as this. But if we move across and we look at it layer by layer as the part would start to print, and we look at the thermal map of the part, we see as we get to the flat part of the top of the housing, there would be a rather large warm area that would happen inside of this part, which would make the part shrink and contract and bring the parts in, which could potentially cause a warpage issue. So if you start thinking about what would my part be like in layers, and thinking about a heat map as you would slice the part, you can change your design in order to avoid that, which gives you better parts. And two different solutions that we see here is one would be a domed and the other would be a corrugation. But when we start to cut the part into 2D layers, and as we get to that larger mass part towards the top, you can see that we're eliminating that area where we would actually have a heat spot on top of the part. And in result, you end up with a better part. There's no real reason for the part to necessarily have a flat top. A lot of times we make it that way just because that's what we're used to designing, but we need to start thinking about the process in which we're designing for. Can it actually have a dome top? Can it be corrugated? It may not affect the end result use of the part. You just need to stick in those parameters and start thinking about on a layer basis what will happen to the part. And if we follow some of these guidelines, we will end up with extremely consistent parts and repeatable parts throughout a build. It improves dimensional accuracy of the parts, and it frees it of any sort of warpage because we're maintaining a consistent balance of the heat across the part across layers. One of the next things that is good to use when you start to design for MJF is when you start to make large mass parts, let's say it's like a 3 or 4 inch thick part, that's going to create a lot of energy and heat. So if we start to look at it layer by layer, we'd have a very warm spot building up throughout the entire part. So what we try to instill upon people is the fact that we should hollow parts out. Think of it more of like an injection molding. We wouldn't want to injection mold a really thick part. We want consistent wall thicknesses. So when we look at MJF, two different strategies that you could use is one is hollowing out a part, right? The other is we could apply a lattice structure either internal to the part where it's not visible, or it could actually be visible inside the part. And these give different things to the parts. One is it's going to save you money, right? Because we're using less agents into the part. We're not fusing all the powder that's going inside of there, so it's going to reduce the price of the part. It's going to majorly improve the quality of the part because as we start to eliminate those heat spots that would be inside the part, we will be able to have a nice even part throughout. So hollowing is a very good strategy when designing for MJF. When we look at hollowing of parts, typically we say you should start to look at hollowing a part when it comes up to about 7 millimeters in thick, right? As we start to go thicker in the part, thicker parts, we'll definitely need to hollow the part out. But a good wall thickness is about 2 millimeters of wall thickness in order to make a good wall thickness for hollowing. So anywhere between 2 and 3 millimeters is a good wall thickness for hollowing out parts. And then when we look at lattice structures for parts, in this scenario we're using a hexahedron pyramid cell. But no matter what type of lattice structure you're using, typically you're going to stay around an 8 millimeter cell size. So the cell size is the shape or geometry that you're using that you're repeating over and over. So you're going to look at a bounding box around 8 millimeters or greater, depending on the thickness of what you're doing. And then you want the thickness of whatever that structure is to be about 1.2 or greater, right? And this is a good balance that we've gone through cost analysis to make sure that you get a good return on it and you get good performance out of the parts. As we started to design more parts for our equipment that we currently have, we started to look at using skeletal structures inside of the part. As we looked at the housing before, this is sort of the same concept. We're going to reduce some mass inside the part. If we look at the top part, that would be more of a typical type of injection molding type design. But why do we have those flat planes inside of there when we can actually just use the structure itself? And as we remove that mass out, not only does it make the part less heavy, it also reduces the part price, and it contains the thermal mass inside of the part as we start to print. So it's just one strategy that we started thinking about as we design parts for our own systems, is if you don't need mass there and it's not necessarily providing any performance to it, then you can remove it and you get better return. This is a part that's out of our 4200 system, and what you see on the left-hand side is the traditional assembly of what it would take in order to make this part the way that we would typically manufacture the part. And it takes multiple components in order to make up this one part. So 3D printing obviously gives you that advantage of combining parts together. And that's what we want people to start moving towards, is when you start to identify parts for a manufacturing system that you're creating, is how many parts can you combine together in order to make it feasible in order for you to actually move to production in 3D printing. In addition to the fact that you can control more of what you're doing inside of the print area. So there's less assembly, there's less costs involved, because we're not having to pay to have each one of these components not only made, but then assembled afterwards. So we have multiple components throughout the systems that we have. We have a 4200 and a 300, 500 series, and now we have the 5200 series systems that have been released. And when we started ordering parts from vendors, our own technology, we don't create them in-house. We order them from a vendor in order to produce the parts for the system. We had to start thinking about how we were ordering the parts. And typically when you would make a build for MJF or any other 3D printing system, you decide how many parts do you need, and you start to fill up your build envelope with the same part over and over and over again. So that is one strategy of thinking about how to fill up a build, is I need 245 parts. I'm going to fill up the whole build with all 245 parts. But we had to start to consider what is the best way in order to fully sustain building these systems. And ordering one part at a time wasn't necessarily the best or appropriate way to order parts for additive manufacturing. So we needed to start thinking about ordering them in sets. So we started using this Kanban theory that's due to automotive, and ordering the entire system of parts that you need for one system to be made up, as opposed to ordering 245 of one, 245 another, is lay out your builds in complete sets, order them in full sets as opposed to one unit at a time. And this improves your manufacturing process, and the fact that we get an entire printer worth of parts out of, or 3 sets in this case, out of the one printer, as opposed to, you get part of your order and then another part of the order later. So it just makes that manufacturing process more efficient, and it can tend to lower costs overall. Another part of MJF is you have to think about how you pack the parts inside of the build envelope. So previously we were just talking about ordering parts in sets, but how do I get those geometries into the sets that I need, and what are the strategies that you would use in order to make those sets a possibility? So one of the things that we previously talked about is the skeletal structures, where we remove the mass, in addition to the fact that it allows you to nest a little bit better inside the parts. One other process that we used was vertical stacking, or solo cupping. So typically this filter housing that you would see on the left-hand side would probably have 90-degree walls, but when you start to think about the strategy of how many parts can I fit in, Do the parts need to have 90-degree angles in order to be efficient for the process of the end result product? We found that we could angle the walls of these parts a few degrees in order to fit more inside of the build envelope, in addition to getting the same properties that we needed for the final part, which allowed us to have more parts inside of the set. Another thing that we started to look at is folding strategies of parts. So on the left-hand side, you sort of basically have the assembly of how the part would snap together. There's a little bit of space left in between, but this would hold a filter. And so traditionally, you don't necessarily think about how many can I fit in and the way can I fit them in. You just take the part in the way that it was drawn, you add it into your build, and then you see how many you can fit in. But when we start to think about maximizing the platform for quantity, we found that if we undo this and do it flat, we still get the same end result part. The spacing's still the same for the movement, but we can fit significantly more into the build. So not only is it about how the parts nest together, it's about how can I put the part into the build envelope in order to maximize the area. The other thing that we started to do is start to look at how do we fit the parts inside of nest before DFAM. So when we took the traditional set before we did any DFAM and nested them in sets inside of the build chamber for the specific product, we found that we could only fit 2 full sets inside of it. But when we start looking at the folding strategy of unfolding that hinge part and doing the solo cupping and adding in the structural skeletal elements to the part, after we did all these different types of things and implemented them into the parts, we found that we could fit an entire another set into the build envelope of our 4200, and that gave us about a 15% cost reduction just by adding that into the build and applying different designs guidelines to the parts in order to get the best performance. So when you start to order parts, there's a couple different things that you need to think about when you're going to make a part in any additive process. One is, can I redesign the part to be better for additive, right? Can we use topology optimization in order to get the same performance and combine parts together? Can we use lattice structures in order to reduce weight and get the same performance out of parts? So one category, do I need to redesign the part? The next thing to think about is, what is the post-process of the part, right? What is the surface roughness requirements that I need? Can 3D printing and additive manufacturing suffice for that category? And what other treatments need to happen to the part afterwards? Is the natural color of the part going to be okay, or do I need to apply a post-process such as a chemical treatment to smooth the parts? Do I need electro? Am I printing big parts and they need to be glued afterwards? Can paint it? And what kind of requirements as far as certifications do I need, and do the parts qualify for that? When you're trying to look at and design for, you need to keep these in mind as you're designing for the process to make sure that they can suffice for using additive for the final part. And one major thing where additive really plays a benefit, whether it's MGF or a different process, is unification of part. Can I take an existing design and combine different components together to now make it feasible in order for me to produce it? Because not in all cases will additive be the way to produce a part for manufacturing, right? It can, when you start to look at injection molding, if your quantities are high enough, that's a good way to go. But if I can then start to combine components together and reduce the amount of molds that I'm going to have to make in order to do injection molding, then additive starts to play a bigger role in the fact that we can be more competitive or better priced in some cases if we start to combine parts together. In addition, that you can get some performance benefits by unifying it together, by not having certain screws or assemblies that go together to have leakage for air. There's a lot of benefits when you start to unify parts. This 140 plus parts is to designate the fact that when we designed our 300-500 series, which is our smaller platform-based system that also allows color, we have over 140 different plus parts throughout the system. And not just because we wanted to say, hey, we can 3D print parts and put 3D printing in 3D printing. It's the machine that makes the machine. It was more the fact that as we start to look at these strategies that we sort of talked about today, and we implement them into it, you really do see performance enhancements in parts by unification, and you start to see a return on the price as we start to apply these to the parts to cost justify the parts being used. So when we say 140 plus parts, that's a lot of parts. That's probably the most parts of a 3D printed in one product, right? So the amount of parts that have been 3D printed in one product. And it's because it made justification sense as far as price when we start to use these additive design features. And currently the materials that we have available are nylon 12 glass beads, and nylon 11. And depending on the product that you're trying to create, they all have different benefits in order to which you would produce the parts in. So if you're looking for a more stiff part, you would move probably more guide towards glass beads. If you need a more flexible part, then you would move more towards nylon 12. And then your all-around material that most people use are nylon 12. When we start to look at basics of designing parts for MJF, we have some minimum features here that we suggest in order for you to use. You know, you can go much larger than this, but this is more saying that this is the minimum area. If we have a small hole that's going through a part, essentially you need to remember 1/2 millimeter. So most small features or things that are going to happen onto a part are going to be a minimum of around 1/2 millimeter. Unless it's a feature such as a texture onto a part, then you can go a little bit smaller, but 1/2 millimeter is about the smallest distance you're going to use either through a through hole or a cutout or an embossing or size font that you would put up. And then you start to look at minimum wall thickness, depending on which plane that you're printing the part in, whether it's oriented up in the Z or if it's oriented flat down in the XY. You can go down to 3 millimeter if it's in the XY plane, or 1/2 millimeter in Z. So essentially, in my opinion, you just go back to the 1/2 millimeter rule. Minimum features are going to be about 1/2 millimeter, but there is sort of a distance of wall thickness about how far it can overhang, because obviously if we made a 1/2 millimeter wall that overhang too far out, then it would be prone to warpage, right? And if we're looking at engraving or putting text onto a part, if we're embossing the part or debossing the part, we're going to probably change the orientation if the text is extremely important on the orientation of which it's facing in the build, right? So if we face text facing down, or any part that's on the bottom plane of the XY facing down in the Z, it's going to have a more rounded over or a smoother process. And if it's facing up in the direction of Z, it's going to have a more crisper detail to it. Reason being is the way that we apply the agents and how many, the way that we fuse down through layer by layer. The facing up surface is the last thing it's going to see is a detailing agent, and it's not going to be fused again. If it's on the very bottom of the part facing down in the Z, it's going to be fused over multiple times throughout the build, and it's going to have a more smooth surface to it. So it depends on what you're trying to achieve with the part. And then if we're looking at different spacings, if we're having an assembled part that's going to move, such as a ball joint, or if we're having pins that are going to snap into place for the parts. Typically, if you're going to have a pin that's going to go into, or a feature that's going to snap together, you're going to look at a spacing of 0.2 millimeter on each side with an overall of a 0.4 millimeter spacing in order for the interference faces to go in. If we're looking at a trapped part that's going to be a movement, depending on the thickness, but general rule of thumb is you're going to have an overall spacing of 0.7 millimeter in order for the part to be able to free up. It's not that the machine can't print a tolerance and spacing in there. It's more about the geometry of what you're doing, because if we look at the part that's on the screen for the ball joint, if we leave a smaller gap, the space will still be there, but the powder will be so compacted and we won't be able to reach blasting out the powder. in order for the part to move. So this is a good spacing in order for the part to free up and allow the powder to get out. But as the wall thickness increases, we have spacing, the heat generated by the part. If we don't increase the spacing, at some point, if the part was really thick, it would fuse the part together. And as I briefly mentioned, as you're kind of doing hollowing parts, some of it is post-processing of how do I remove the powder out of the part, right? If I'm trapping the part for movement, if the part is going to be a hollow-walled part, as we talked about before, do I need to remove the powder out of it if it's a hollowed part, right? Maybe I need to leave the powder inside of it, which is fine. We don't need to talk about strategy of exit holes. But if I need to recover the powder inside of a part, this is what we're denoting here, is putting a exit hole or multiple exit holes in order to blast the powder out or drain the powder out of the part, right? So it's just sort of a strategy. Not only are you thinking about how to design the part for the performance, but also how am I going to clean the part afterwards, and what do I need to do to make that easy for the process that you have, right? And then if you start to do ductings, there's strategies out there for building chains or pull-throughs because as we all know, your blaster is not going to go make a 90-degree turn or the powder gets so compacted inside of there that if we pull a chain out through it, once the powder starts to collapse, the blasting won't find its way through in order to clear out the whole duct. But if we don't put something inside of it in order to remove some of that out and start the collapsing of the powder, it can be very difficult to get all of the unfused powder out of a part without some of these strategies here. So with the 4200 series and the new 5200 series, we have a printable area of 15 inches by 11.2 by 15 inches. And there are going to be many cases where you're going to want to build a part that will be larger than the build envelope, right? So we're going to cover just quickly some strategies for bonding parts together. With like any additive process, as far as polymers are concerned, you need to know the type of polymer that you're using and what strategies you can use for glue joints and the type of glue to use. So here are a couple of different types of recommendations that we have as far as bonding parts together, whether they're going to be end-to-end, right? One would be a dovetail or a jigsaw, depending on the type of software or how people use the term. But it's more of a dovetail joint. The more surface area that we have, and the reason you would use that type of strategy for a joint is that if you are going end-to-end, you don't necessarily just want to butt two faces together. We have more interference surfaces here if we cut it out as a dovetail, which provides a better bond for the adhesive. The overlap is a very good option if you can afford to overlap the backside of a surface. So like if we were making a front end of a car and the back end side of it didn't matter as far as the looks were concerned, and you could still fit it in with whatever parts are going behind it, an overlap would be a very good choice and a very good bond, because not only we're getting a lot of surface area that are bonding the two parts together, or if it's a really wide area that's going to be need lots of different areas, you can do the multiple dovetails. And then just a little bit closer look at the offset. We have different recommendations for these, and at the end we're going to have a link that will show you that we've announced the MJF handbook, and a lot of this information and a whole lot more information can be found on that site in order if you're going to go into a specific detail. So some of these numbers are just kind of pulled from there, but it just kind of gives you a good idea of the type of information that you'll find there. And then some of the recommended types of glue. We've worked closely with Hinkle or Loctite, and the two that we mainly prefer, if you don't need a really superior bond strength and you need to do it very quickly, you're going to use the Loctite instant bonder, which is essentially a CA glue formulated for 3D printed parts or additive manufacturing parts. And then if you need a stronger bond, then you're going to look at a universal bonder, which is like a hybrid glue of CA and different types of epoxy. And then if you need the highest structural, then you will go to a polyurethane or epoxy and use the Loctite 4080 or 4090 or a similar product. It doesn't necessarily need to be Loctite, but these are the ones that we've found that work really well. And then to our last section, we're going to briefly go over threads and inserts, mainly inserts. So MJF readily available will use or accept using different types of inserts. So if you don't need to print a thread, and printed threads are okay in certain circumstances, but inserts are going to be a much better option depending on the connection that you need and the force that you need to use it with. So we went through a lot of different types of testing, and the three that you see that are circled, the red, the yellow, and the green, are the three that we focused mostly on. And the best ones that we have found is the heat staking, and then we would move up to the steel twist, and then the flange screw expanding type. You can print threads with MJF. You can go down to M4 or M6, and they work fine, whether you print it in the 90-degree orientation or 45-degree orientation. But when you need a stronger thread or a tighter thread, depending on how much screwing in and out that you're going to be doing, we would recommend an insert. And just a little bit better, it depends on the application of what you're using, but the best results that we've found are through heat stake inserts. They have the best torque out as far as the parts because you're essentially melting that insert into it. Okay, and now we're going to come into closing and answer any questions that you guys might have. And as you can see here, here's the link to go to the MJF handbook where you can find this information and a lot more information on applications and design strategies. Thank you.
Thank you, Justin. We do have a couple of questions. First one, can hollowing out a part or adding lattice features, is that something in the printer software or is that third-party software?
So as far as hollowing out a part, hollowing can happen inside of the software that we provide. So our SmartStream software has the function in order to allow a wall thickness for a part to be hollowed. As far as lattice structures are concerned, you would use a third party, either your CAD software that you're currently using, or you would use NetFab or Magix, or those are the two most popular third-party softwares for additive manufacturing.
All right. And you mentioned solo cup stacking. How far apart do the edges of the parts need to be from one another? Right.
So typically the larger the amount of space, typically when we would just do a generic part, we would do about a 5 millimeter spacing in between parts. But when we're going to go and solo cup a part, we're probably going to go to 8 millimeters just to give it a little bit more spacing. It really depends on the size of that part, right? The larger it is, the more spacing we're probably going to want into it. But that in that particular case, it was probably anywhere between a 5 and 8 millimeter spacing on the part that we saw.
Okay. What kind of equipment is required to handle the powder? Is it toxic?
So the powder is non-toxic. We have white papers on the amount of powder that could be in the air for the air quality, and it's perfectly safe to use it with or without a mask. We always recommend using a mask. The processing that comes with the system is a processing station. And the processing station for the 4200 and 5200 series will extract the powder out of the build unit, but then afterwards you would always have to have a bead blaster. We typically use glass beads or different types of media in order to remove the extra powder that's still onto the parts. And that doesn't matter, it doesn't matter which series printer you're using, whether it's 300, 500, 4200, or 5200, you always need a bead blaster to get to the final surface.
All right. You mentioned that the machine adjusts temperatures as it's printing. Does that mean that it fixes fusing problems as it's printing?
It's more maintaining That's a tricky question to answer. It's more maintaining the bed temperature to make sure the fusing is happening properly, right? So as it's scanning to making sure it can make slight adjustments in order to make sure that it's fusing appropriately. But it's not going to drastically change what it does. So it's going to do calibrations before it starts to make sure that the melting point is happening. It's more mapping out as it goes that there's not major changes in the bed temperature. And that way we can use the heating lamps to maintain proper bed temperature to promote the fusing.
All right, and last question. Powder-based machines are often characterized as messy. Do you have any experience with binder jet or SLS, and how does it compare to the MultiJet Fusion?
Right. So every one of those processes is a powder-based process, right? So I would say that MultiJet Fusion is a much cleaner process than compared to SLS due to the processing station itself and the build units themselves, because the build unit is essentially a cart that goes into the machine, and it can be completely closed off. So as soon as it comes out of the machine, you put a cover on top of it, and then you wheel it over to the processing station, which will auto-extract a good portion of that powder. And also inside of that processing station, there's laminar flow to keep the powder from coming out. So for a powder-based system, it's extremely clean. But once again, you are dealing with powder, and if you're not handling it properly and someone throws something into the powder, you could have a cloud of powder come up. So it's more about the operator, but the system itself is very self-contained as far as keeping it clean.
Okay, we actually have one more. If we have parts that were designed for injection molding, can they still be printed on the MultiJet Fusion, or do they need to be changed or redesigned?
In most cases, all the practices used in injection molding will fit very well with MJF. Someone would still need to look at the design itself, but there's a very high likelihood it would just transfer over. It really just depends on the design itself. But in most cases, those same rules apply and are very good for MultiJet Fusion.
Excellent. Thank you, everyone who's joined us this morning. It looks like that's all the questions. And thank you, Justin, for presenting and fielding the questions. If you're interested in seeing these HP printers and having a more hands-on experience, we have a technology showcase coming up on June 27th at TPM in Charlotte, North Carolina. This will be a lunch and learn type of event. We'll do a tour of the printers, and we will have an HP 4200 and HP 580. We also have some upcoming webinars as part of our manufacturing webinar series. The next one is on June 11th. It is growing a spline with SolidWorks, and we also have one on July 9th, which is titled One Step Beyond with 9-Dot Connects, which is a PCB design focus. Thanks again, everyone, for joining us. Have a good day.